Well, can I start?
Yes, sir. We're waiting for you.
Everybody here? I believe uh, this one, which is the designing filter media, that's actually my area of expertise. So the introduction part, Professor Mukherjee, he already covered the introduction part. So I'm going to cover detail of the multi-layer construction, how you can do it. That's the key portion of it. To me, this is really important one. You know, what is pattern? Pattern means protecting technology. That's one. What about the other? The other is uniqueness, which means no one has it. However, once it's patent, then you have to have license to use it. But you do have license already because I'm giving you the permission along with the department, textile department, anything working for textile department. I can give you the license so you can use. The equation that I have is really, really applicable to the round membrane. Huh? Yeah, because they use the same kind of membrane and several layers of it, right? So you can actually calculate absolute the rating using that equation that I'm going to give you. Actually, it's right here. It's right there. Yeah, right there. Yeah. So to me, the right now, I think I'm the only one who has the theoretical background how to design the multi-layer, the high efficient filter media. So that is my core subject for today. But beforehand, somehow you have to go over some basic information first, so that you can understand better. The introduction part, I believe the Professor Mukherjee, he already covered basics of it, like define the filtration objective and purpose and type of solid liquid. You have to know, determine the key filtration parameter. He already covered those. Then select filter media type. He also covered this one. I believe he did cover this one as well, right? And property, pore size rating, thickness, performance evaluation. But 7 is quite important, the compliance and standard. Probably that one I may cover really briefly last day, testing and evaluation section. So it's repeating the microfiltration 0.1 to 10, ultrafiltration. And then the application here. ePTFE, to me, this is a future direction, even though they call it PPAR. However, ePTFE doesn't have any water see, there is no dissolve in the water, any portion of it. If some portion of dissolve in the water, then you have trouble. But currently, the issue is ePTFE. PTFE is forever chemical. There is no way we can landfill because it's not biodegradable. That is issue. However, PTFE, we are not using a lot, really small amount, probably screen that we use to support PTFE might be a little bit issue. But to me, the ePTFE is future directional membrane. You know why? The fiber size is quite small. Second, fiber itself is quite strong, really strong. Third, manufacturing process is a lot easier than normal the membrane process. The other, uniformity. That is a big issue for me. So to me, the ePTFE gonna replace all the current membrane will be replaced by the ePTFE. That's my view. So the ePTFE, without ePTFE, medical field, they have a bunch of trouble. They are using a lot. Even when you do the tooth planting, implant, and then they do use a lot of the PTFE, ePTFE, too. That's one area. Also, a lot of the inside when somebody operates then they do use a lot of PTFE as well. So PTFE, without PTFE, medical field, they have a bunch of troubles. Huh?
What's the difference between ePTFE and PTFE?
ePTFE expanded. I'll show you later on. I'll show you. So water treatment, currently they do use food, beverage, chemical processing, medical devices. Wait a little bit. Here. This is stretched PTFE. Say you have to extrude the PTFE and then make sheets. And then they have to stretch machine direction, and then they have to stretch the transfer direction. We normally call it tenter, T-E-N-T-E-R, tenter machine. Then you can stretch so-called biaxially, simultaneously stretch. I don't know whether you notice that. This is a 30 micron bar. How small fiber is. Also, look at this. the uniformity-wise. To me, currently, however, this one, I did it myself. In fact, I associate several companies, currently 3 companies. So they already have the PTFE stretching line. They're already producing the sellable ePTFE. One in Japan. Actually. Huh?
Company names?
What?
Company names?
No. No. I'm not supposed to. Yes. So I do have some patents on PTFE too, stretching patent. Well, that's why I'm still working, traveling and working. So I don't know whether you notice or not. This is ePTFE. This is ultra high molecular weight, high density polyethylene. So they try to duplicate the ePTFE, but they are still doing it, but it's not really possible. I don't know whether you notice or not. This is the best material so far. Yeah, compared with the ePTFE, still lots of issues. Yeah, there are a lot of void there, void. Even though it's 10 micron, almost same size, same size. No, same magnification. But still, the high density polyethylene, ultra high density polyethylene, is far below. So this is what I stretched. I actually spent about 3 months to produce something like this. But normally, this is what you see, like this. Fiber and some knots there. But still it's okay. If there are some knots, something like this, then the machine gonna be a lot cheaper. But if you like to do a lot of fibers in it without knots, then machine cost is a little bit higher. This is the ultra high molecular weight, the high density polyethylene stretched. They compare with ePTFE. E means expanded. Yes. In fact, this one is currently commercially available for liquid filtration. Now, well, you already noticed that the round, the cartridge, several layers of it, right? It's not single layer, but same membrane, but it's several layers, not single layer. Then how actually you can calculate out the better absolute rating? Huh?
What is this slip flow effect?
Oh.
Slip flow effect. The first line examination.
Less pressure drop. due to slip flow. I'm sorry. Mass pressure. ER should go over there, not there.
What is slip flow?
Huh?
He's asking slip flow.
Oh, this is kind of the academic jargon. The slip flow is flow is going over the fiber. Huh? Normally, if the flow touch with the fiber, it stops there. But fibers are really tiny, it actually slips go over. It's not stop. That's actually the kind of theoretical the calculation wise. So if the slip flow occur, then pressure drop quite low because it stops there instead of slipping over. So that one, if I want to explain it, I need to put in some equations. So it's a little bit complicated. So the important thing is a tailored pore size. So liquid filtration, pore size distribution. Oh,
So if fluid will fluid will slip over the fibers, then filtration efficiency also reduces.
here, I'm not talking about filtration efficiency. I'm only talking about pore size. Pore size. See, liquid filtration, the pore size is key. The air filtration is different. Air filtration, fiber size is important. Yeah. When liquid filtration, the pore size is key. So all the equation or designing equation, everything relates to the pore size. We normally call it mean flow pore. So there is some distribution of pores. It's not single like that.
Actually, the nanofiber offer the larger surface area. Okay, so from that, if you see the larger surface area, resistance will be more. That is the general principle. Whenever I talk about the seed flow, that is for the gaseous molecules. Gaseous molecules are so small that it can flow fast. It is not giving you the resistance that way. Normally, the surface area applicability is up to a certain extent. But if you are going for nano range, that is not so much applicable over there. Are you getting my point? Normally, if you take the coarse fiber to relatively fine fiber, you are having larger surface area. Larger surface area will give you the higher resistance. Higher resistance means higher pressure difference. The nanofiber is having such kind of very fine, so that the gas molecules also can slip past, because the gas molecules also plays a vital role for pressure differential. So you cannot straight away equate like the larger surface area, because nanofiber surface area will be many scale higher. Okay, so but the permeability is not that extent lower. Are you getting my point? Permeability will not be in that scale lower, because the gas molecule will be able to flow fast. Because I am talking about glass molecules. Okay, not the particulate matter. Gas molecule will be flow fast. That's why it is not to that extent. Resistance obviously will increase, but it will not extend it will not extend to that extent, to that degree.
Well, he's correct. The basic theoretical approach around the fine particle, fine fibers and slip flow, that theory developed under air filtration area. However, the liquid filtration, viscosity is a lot higher, density is very high. So I believe it works a lot better in liquid filtration than air, I think. Why epitaph extended? Certainly, nanosite. Huh? So 38 nanometers up to 200. Actually, that I measured is a lot less than 30. Hydrophobic, excellent chemical, and superior cleanliness. He's talking about the dirt removing layer. You compare with the epitaph, it's not really comparable because epitaph, once you put it on the surface, the whole thing is super. Why?
Because of nanopores.
The surface of the epitaph itself. Here, I don't know whether you notice some sort of the wheels made of the epitaph, something like that. And then there is no mamo. What do you call it? No, that is terminology. We sometimes measure that one. What about smoothness of the rubbing? Rubbing is yes, PTA fiber. Ah, yeah, your friction is friction coefficient is really low. There is terminology for that, but I could not remember. Anyway, that's a good one. Long service lab. Right there. Low coefficients of friction. Right there. Excellent dielectric. Low electrostability charge. However, if you like to produce the epitaph, this is not easy. You have to have some sort of sellable product, but normally it takes 5 years, starting from the coming out of the sellable product. Also, you need to have some hands-on people as well. So it's not that easy. Now I'm going through how you design the multilayer media. So this is basically first layer is coarse layer, and going down tight layer, something like this. The other thing is, if you're gonna separate the layer, or if you're gonna adhere each other, bond each other quite, then the characteristic is a little bit different. Sometimes you use some sort of the support layer in between. So round cartridge, sometimes they do that way. Here, this is interesting one. That is coarse layer, looks like this. Blue one is fine layer. If you combine both of them without having any space, then you have this one. So, in fact, mean flow pore size is going to be a lot smaller size. If you have some space in between the layer, then this is what you see, like this, red one. So this one is part of this characteristic. That one has part of that characteristic. I believe you understood. Huh? Tightly bonded and loosely bonded characteristically different. Yeah. Well, I don't know whether I'm going to go through some mathematics. Yes, Hagen-Poiseuille equation. Well, just like what somebody asked question on the first day. This is all bundle of capital, the assumption. Assumption, yeah. Now, from that, the quartz layer with the largest pore should be thicker than, why? See, yesterday, I actually modify everything, but somehow I couldn't find my file. But anyway, the thickness of next layer should decrease as pore size decrease in order to increase the life of filters. So the mean flow pore size and the air permeability of well-laminated multilayer media can be calculated with the property of individual layer. That's the key point. So, you know, the tortuous path, non-move on anything, is there is tortuous path. Then how we can assume the tortuous path, actual the distance of travel? This is really tough, but however, there is some assumption. If you know the porosity, then 1 over porosity is tortuosity. So let's say porosity 1 over 1, then tortuous is 1, then it's going through fast. So somehow you have to measure what? Porosity of your material. Do you know how to measure it? I have something there. Actually, I modified my presentation last night, this morning, so that you can have your own lab. Also, I insert several drawings. So you already seen, it's not yet perfect, but how it works, right? So from that, you can build your own lab if you have money. Anyway, I'll show you. So, if there is the double layer like this, then if it is when you look at it, then the pore, you can small pore, because it's, oops. Right here. This is porosity measurement. You have to use the wetting solution. Cut 1 centimeter, 1 centimeter, and measure the thickness of sample. They calculate the volume and weight of the sample, and immersing into the wetting solution, and weight it, and weight the solution and the volume of pore, and then you can actually calculate the porosity that way. So it's quite simple.
Sir, why we have chosen a fluorinated solution in this case? Why not water?
See, somehow I didn't give you some the way to measure the contact angle. The contact angle is quite important. If you use the water, then there are some probably a lot more error than wetting solution. Wetting solution means it wets all the surface of fiber. Huh? But water content is quite large. It won't cover the surface of the fibers, which means you have some curvature like this. So there are a lot more error than wetting solution. You can use water if you want to. But however, when you handle it, you're going to lose a lot of water out of the media itself. It's not going to stay long enough. I hope you understand.
Another point is that water, you have to see whether the fiber swell in water. If there is a swelling, then obviously the pore structure will change. Okay, during the measurement, that also should be taken care of. So if you are taking with the help of polyester, it will not swell. If you are going for cotton fiber, it will swell. That void will change.
So this is what I do. Actually, not I do. My lab people, they are doing it this way. So you have to use the Laplace equation, and then you come up with this one. This equation is key equation. So make it simple, right there. The D is overall mean flow pore diameter, D. What about the lowercase d? This is mean flow pore diameter of ice layer of individual layer of the mean flow pore. The other one is epsilon is porosity. So you have to measure each layer if the layer is different. Huh? If it is single layer, use the double layer, making double layer, triple layer. Then you don't have to. This is the double layer with the same membrane material. Then overall mean flow pore is 0.5 individual layer of the pore, mean flow pore divided by the square of porosity. What about the triple layer? Oops. The triple layer is something like that. Actually, this works. So then how you're going to make the tailored multilayer microfiltration media? Actually, this is not microfiltration media. The membrane media might be better. So you have to have target. Whether you're going to make 0.1 micron size or 0.001, and then choose first layer. Most likely, currently they are using same layer. Anyway, so this is the actual result. Single layer pore size distribution like this, and then porosity is 97%. Then if you do the double layer, then like that, it's about 2. Once you use the equation up there, it looks like that. So when you look at it, it's really close close to the actual data. This is the triple layer. The porosity is a little bit lower. However, if you use the same equation, you can predict almost same one micrometer. So that's the design of multilayer media. The detail is here. Also, I gave you two other my old articles. Yeah, articles. If you combine those two, then you could understand this one a little bit better. So from now on, viscosity issue. The liquid filtration, one of the important property you have to know is viscosity. So this viscosity is somehow the function of temperature. So then we heard about a lot of the viscosity. Also, you can buy some equipment to get some viscosity value. However, this is what I really want you to do it. That is, yesterday I gave you some equations, what to do. Yeah. Yeah. So this is the dynamic viscosity measurement. And then the principle here is capillary rheometer principle. So my graduate, master, and PhD dissertation, I use a lot of the capillary rheometer or some other rheometer. So we call it the rheology. The blood rheology is currently really popular. Polymer melt rheology or polymer solution rheology is quite important too. So if the liquid filtration, somehow you want to know the viscosity of it, then this is really quick also, because once you measure the viscosity, that's not really shear viscosity. So if you really like to know, it's not really static viscosity. You want to know shear viscosity. This is how you're going to do it. Here. This is diameter of capillary. This is the length. We used this equation yesterday in order to get the shear viscosity. So shear stress normally eta, but if it is the so-called power law, then sometimes K, but it's same as the viscosity. Well, here, I already brought, again, this one. The region that I brought here. This is what you need to do. Balance need to connect to the computer so that you can get the weight as a function of time. That's important. Weight as a function of time. So it has to be connected to the computer. Way. I don't know whether you notice or not. This is more likely this chamber and capillary. So I'm going to give you detailed dimensions so that you can build. I don't know whether it's possible or not. I hope you could. Okay, that chamber is actually this one. This part, understand? That's this one. This one is slurry. So yesterday what we did was to try to come up with some viscosity, but actually you can use it as the liquid filtration device. Constant rate, constant pressure, work, anything you can do with it. So this part right here is same as this one. Yeah, you have to build something like this on top. Then actually you can carry out your the liquid filtration testing equipment. So I'm giving you all the drawings. It's up to you to build the test rig. So this is actually what I did, experimental data. The lube oil 50W40 that I used it, and new oil, used oil, sample that I used microglass, melt-blown cellulose. So somehow I like to look at all the characteristics. So shear viscosity and volumetric flow rate. This one we call it millipore pressure millipore holder. Actually, millipore pressure holder. I don't know whether this is commercially available right now or not. I doubt it. And then this is the final result. Yeah.
What was the full form of MFP?
Huh?
MFP?
Mean flow pore. Mean flow pore diameter. Mean flow pore diameter. There is equipment. You can buy it. It's about $20,000. Then you can get the mean flow pore right away. But how? Yes, mean flow pore is quite important for liquid filtration. Yeah, that's the starting testing equipment, mean flow pore. So here, microglass and melt blown and Q, you can measure it, right? You can measure that one. I don't know, the Q value, right of 0.2. But important thing is final result. Here, Q and time. So you can actually get some differentiation between used one and then some the additive 1 and additive 2. I don't know. It is not really interesting to you, may not be. So here, this is quite interesting result. Q times viscosity, then you can get all 4 different material as one single line. Then you can get some conclusion out of it. So it's possible to measure shear viscosity of lube oil using millipore or pressure holder. Polymer 1 additive appear to be much more effective to reduce the viscosity than polymer 2. Flow rate through the melt-blown filter media was slightly increased at the higher pressure, even though the air pressure was increased 2 or 3 times. This is the issue. The melt-blown, if you pressurize a lot, then it's compressed. So that is the bad part of the melt-blown material. But melt-blown is quite popular right now. I'm going to talk about that one in the sustainable filter media development. I believe this is the last slide that I have. However, I told you earlier, this is my expertise field. So I hope you could use in your field. But like I told you, you have a right to use that equation. It's big privilege. I don't know whether you notice or not. Yes, it does. Finish a little early.
You can discuss if you have any questions.
Well, here I really want you to study the material that I give you. So 3 of them, sometimes
Is there any equipment that prepares this like EPTFE? Is it commercially available? Yes. The PTFE is there. But EPTFE.
No, EPTFE is the next to that. EPTFE is also available, but there is no Indian manufacturer at this moment. India basically imports the EPTFE membrane from abroad. Presently, we don't have any EPTFE system.
EPTFA, making EPTFA is not that easy. Somebody who knows about the process, then it's a lot easier. Well,
basically, it is expanded to get the sufficient strength to the material. That is the basic idea. Choose to make UHMW HDP membrane.
UHW.
Ultra high molecular weight, high density polyethylene membrane. What technique? It's
Same thing.
Or electrospray?
No. It's same stretch. Stretching. It's not melt-blown, it's stretching. Same as EPTFA. I can tell you. Well, it's recording, so I don't want to. Later.
Teflon, it is basically Teflon. the thing is that it is in a, I mean, fibrous form. It is not a coated form.
Coated.
If it is a coated form, then the problem here that the pressure will be very high. That is why that is the challenge again. How to make a membrane